What's up, everybody? So today we're going to do a little differently. Instead of doing Khan Academy, I'm just going to film myself kind of going through some of the notes. So what I would suggest to people that have printers, print this note packet up and fill it in just like we would be doing in class. All right, follow along, fill in the notes, pause the video at any time to give yourself an opportunity to solve the problems independently, and then click play to see if your answer matches the answers that I'm going to write up. If you do not have a printer, don't feel the need to rewrite and reinvent every single process of these notes. However, I would definitely have the answers and some of these solutions jotted down so you can go back to refer to them. Always, you should be using this video and your notes as resources in order to complete your independent practice that you'll submit back to me for grading. All right? So without further ado, welcome to class and let's get started. So today we're going to be talking about how to solve exponential and logarithmic equations. Now, we've been working with exponents and logarithms for a couple weeks at this point. So here's our first step. We're going to be solving this in a couple different ways. There's called the equal powers property, the equal logarithms property. We're going to be taking logarithms to each side. We're going to be doing this thing called exponentiating a problem. We'll cover that a little bit later. For the equal powers property, this is a definition. It states for b, and b is just a number. For b is greater than 0 and b is not equal to 1, if b to the x equals b to the y, then x equals y. What that really means in a nutshell is, if we have an equation that has some number being raised to an exponent equals that same number being raised to an exponent, well, the exponents are equal to each other then. If the base is the same, these exponents must equal each other. So, check this out. We got a problem like this. 6 to 5x plus 2 equals 6 to 3x minus 2. Well, we're using the equal powers property. We notice, well, the bases are the same. Since the bases are the same, what really happens is it's like canceling these bases out. Now, by definition, what we're really stating is we can set the exponents equal to each other. But if you want to say like, oh, the bases cancel each other out, I would understand what you mean. Even though that's not quite the best math vocabulary there, but for our purposes, yes, they're the same base, just cross them both out and set the exponents, or what's left over, set them equal to each other. Now, this is just an equation that we would solve in the same way since, Algebra 1. Let's get all of our all of our variables to one side and all of our whole numbers to the other side. So we can subtract 3x and maybe minus this 2. If I rewrote all this, I would have 2x equals negative 4. Solving this equation, we can divide both sides by 2 and get x equals negative 2. And that's how we would solve using the equal powers property. Continuing on with this process is we can solve doing a problem like this. You can also go back and plug this back into the original equation if you want to check the math. If I want to do my equal powers property again, look at the setup of this problem. The bases are not the same. So it might lead us to be discouraged and think, oh, I can't use the equal powers property. However, that's not the case. We can actually still apply this equal powers property. But in order to do so, I need to have the bases become the same. How do I do that? This is 3 to a power. This is 9 to a power. It might help to recognize that 9, well, I can rewrite 9 and kind of get it related back to this 3. Maybe you're already thinking about how to rewrite this, but if you're not, it might help to have this jotted down. 9 is the same as 3 squared, or 3 to the second power. So I'm going to change this 9. I'm going to swap that 9 out. I'm going to swap this out and write as 3 to the 7x minus 3. That's the left-hand side. And I'm going to replace this 9 with a 3 squared. It still has the exponent of 2x. So I replace this 9 with 3 squared. Now we might notice, oh, the bases are the same. That's what we need to have. Before I go ahead and kind of cancel out the bases, again, not the best math vocabulary there, but before we set the exponents equal to each other, I'm just going to simplify up here. A power raised to a power, we simplify by multiplying these two together. So we have 3 to the 4x. We can cancel out these bases. Like I said, the real proper math vocabulary is set the exponents equal to one another. And now we can solve. Solving this equation, we can bring the 7x to the other side of the equation. We have negative 3 equals negative 3x, or that would reduce to x equals 1. And that's our solution using the equal powers property. All right, now, sometimes it's not going to be possible. Like this problem here, 6 to the x equals 27. I'm not going to be able to rewrite 6 or 27 to have the same base in order to do that equals power property. So we're going to need another option. One of our other options is to take the common logarithm of each side. So to take the common logarithm of each side, this is what that means. It means I'm literally going to take the log of each side. Think back to Algebra 1. We used to say things like, whatever you do to one side of the equation, you have to do to the other. Well, that's basically what happened here. Logarithm is an operation that we are putting on both sides of the equation. So I'm taking the log of 6 to the x power and the log of 27. Now, we're going to solve this. In order to solve this, it's useful to recall some of my logarithmic properties, such as x can be rewritten as putting x to the front. That's from our expand and condense section. This exponent can just drop right to the front. Now we have x log 6 equals log 27. Divide both sides by log of 6. Remember, log of 6 is just a number. Now, this is going to have a decimal answer. That's why I'm writing the approximate symbol instead of the equal sign. We would actually have to type this into our calculator. Log 27 divided by log 6. Go ahead and you can type it into your calculator now. I'm going to round my answer to the nearest hundredth. Rounding my answer, I would get x is approximately equal to 1.84. If you didn't get a chance to do so in that problem, for the next problem, don't forget, you can pause the video at any time, give yourself an opportunity to try some of the problem on your own, and then hit play to kind of check your work. Might be a good, useful way of practicing and getting some good instant feedback from me. All right, our next problem, we're going to do the same type of example. All right, we're going to do the same example, a little too far, of taking that common logarithm. To take the common logarithm of each side, we do log we have the log of each side. I can then rewrite my problem by putting 5x minus 2 in the front. I'm taking the exponent and putting it in front of the equation. Now we can go ahead and solve this problem. First off, it might be useful to realize that log of 10, and I'm going to put parentheses around here to indicate that's all being multiplied. Log of 10. The log of 10, this is log base 10. This is 1. A log with the same base, they will always be equal to 1. So that's equal to 1. But maybe jot a little note up here for you guys. Log of 10 equals 1. Since that's equal to 1, we can just cross that right out because 1 times anything is just the same number. We can rewrite this as 5x minus 2 equals log 44. And you can proceed to solve that problem. I'll leave that one to solve for you guys on your own. But if you want to check your work, you should get that x is approximately equal to 0.73. Now we're going to move on to the equal logarithm property.